We're excited to have our very own Steve Davids here today to teach us about search concepts and tools. Steve is a contributor on the Apache Solr project and leads a team that has developed a large-scale distributed search application using Apache Solr.
So today, I'm not going to be preaching about Solr. Instead, we're going to take a step back and just learn about the concepts and the tools and the search concepts that deliver search capabilities. And what we really want to do here is have everyone understand how to demystify search. You know, what algorithms can we actually implement to make search fast? So I always like to take a step back and ask the question of what is search, right? Who has a definition in their head? Anyone? Just yell it out.
To look for something.
Sure. How about from a technology perspective? What kind of technologies can you use to perform search? And let's not say Solr. Let's try something else.
Oracle text.
Sure, Oracle text. grep, exactly. Grep works great too. Grep minus I. Right, Google, sure. All right, so I did a Google search to see what the definition is. So who wants to read that out? Dan, go ahead and read the definition.
Try to find something by looking or otherwise seeking carefully and thoroughly.
Yep, seems reasonable to me. The interesting thing that I saw with this was the synonyms. I thought these were fantastic synonyms. One is hunt, look, and quest. So, you know, what can that distill down into? All right, the first bullet here, who's seen code like that? Right? Yeah, sure. We can throw a MySQL query in there, and we can just say wildcard name. Just give me everything. I don't care. All right, that's one way of hunting for some information. This one, the bottom one, you might not actually see all that often. This is actually Leucine syntax. And what I'm demonstrating here is if a user is trying to find an article from the Wall Street Journal, look at all the possibilities. This is very tedious and very frustrating from a user perspective. But I do see users actually doing this, which is a shame. So hunting is kind of the bare bones minimum search capabilities. Let's look at the next thing. So how about look? So look, this is kind of where we're starting to see a lot of search interfaces, right? So we want to look for information. We don't want to hunt for information. We want to put in some basic information, and let's get some facets, right? So for this example, I was looking for a TV, and yeah, I want a 70-inch TV because I just want to be ridiculous, and 4K Ultra, right? Now, I want to see what brands are out there. So I want to select Samsung, Sony, whatever. And that's more capability of looking. I don't need to search specifically for Samsung. I can just say, I want a TV, and please guide me through the rest of the process. Let's make the user experience good by providing these facets. Also, with the look capabilities, we have relevant results, and we're going to use signals to boost relevancy. We're going to talk about that a little bit later on of what is relevant and what does boosting actually mean. And also the ability to quickly whittle down results, and that's more of the facets that I was talking about earlier. And then quest. All right, so quest is actually a fantastic way to go through the progression, right? This is a higher level of provide recommendations. So sometimes the user doesn't actually know what they're looking for, but based on their historical context, let's actually see if we can give them the right information that they're seeking. So in my example, this is my Amazon Instant Video examples, and they've got me pretty good, right? So I like history, I like action. They got me pretty good. And also when I'm bored, I'll go to Twitter trends and actually see what's trending on Twitter just to see what's going on. All right, so I kind of distilled down these different categories. So we have hunt as MySQL, so that's kind of let's generate the SQL query. And yeah, MySQL, SQL commands is a form of search. I wouldn't say it's a higher level form of search, but it is a form of search. Look is Solr, Elasticsearch, and Blur, which is what we're going to be talking about a little bit later on. That's kind of the happy medium of providing those capabilities for faceting, filtering, and actually pulling information down and guiding the user. And then quest. So I put Mahout in there. That is a machine learning technology, and that will actually provide recommendations. It is important to note that Solr, Elasticsearch, and Blur, they kind of cross-pollinate. So you can write Solr queries that is on the hunting side, and you can use Solr to do quest side. So they provide more like this capabilities. I'm looking at this document, show me relevant documents associated to this. But like I said, they're happy in the medium here. So who wants to guess what this blue box, what they all have in common? And it's their core technology. Anyone? Leucine. Fantastic. Yes, Leucine. So what is Leucine? It's really just a Java API, a bunch of Java jars. That's it. That's all you're going to get. So you're going to download the distribution, get these Java jars. And so what do these Java jars do? They provide free text search. And what I mean by free text search is that we can chunk up words and actually provide small capabilities and search word by word. Relevancy ranking, we're going to talk about that a little bit later on. But they have relevant algorithms to boost stuff to the top to bring the most relevant information to the users. Faceting and filtering, which is what I've already talked about a little bit with the Amazon UI. They provide APIs to both display the counts and the values and the ability to drill down on it. Hit term highlighting. So in Google, when you provide a Google search, you'll put in some keywords and then you'll have a link and the words underneath it with something bolded, right? That's hit term highlighting. So you get a little snippet of why the thing matched and provide you a little bit of context if you want to click through on that link. So they provide those capabilities. Near real-time indexing and querying. So this is more new since Leucine 4X, where you index it and it becomes immediately queryable. Before you had to actually do a hard commit, and it took a little time for the results to actually show up in the index. And finally, it provides a inverted index, and this inverted index provides the speed of searching, and we're going to talk about that a little bit later on of what that actually means. All right, so we're going to talk about the capabilities for searching in Leucine, right? So what kind of capabilities can we use to retrieve information? So the first one is keyword, right? So keyword is, I'm just going to put in a bag of words. So let's say I want to search for bti360.com, right? So I could just search for BTI360 in Google, and that's it. It also allows you to do Boolean operations, so you can do ands, ors, or nots to kind of hone in on that information. Next is Wildcard. So Wildcard allows you to mutate and find different variants of words. So if we look down here, I've got walk star. What a star means is 0 more characters following that. So this is going to find walked, walking, walked, that sort of a thing. It also allows you to do question marks, which means any single character. So this is going to find a couple variants of Muhammad with an O and U and AED. And they also provide a regular expression query syntax. So in here, I can be a little bit more specific where I say, OK, it needs to be OU. The M is optional and either an A or E. So you get a lot of different variants for a regular expression. All right, so proximity queries. Proximity queries are if you're trying to find a phrase, right? So if we want to say the quick brown fox jumped over the lazy dog, and we want to quote that, we're going to say, we're going to make sure that every single word is right next to each other, right? The other capability that you can do is say, I want to see Steve and David's is within 3 words of each other, or 2 words within each other. And that provides the capability of maybe my middle name shows up, right? So we can still find that match for Steve David's in there. Fuzzy. All right, so fuzzy. Fuzzy it uses the Leucine edit distance. And so what it allows you to do is say close enough, right? So you can specify the number of edits that can take place. So for the example from Muhammad, I could just say Muhammad the original way that I think it should be, and then I could just make it a fuzzy search, and it'll find variants. So the example that I had there, it had 2 edits in it. It would actually find both those variants because of that fuzzy search. All right, so a range query. A range will allow you to specify, this is for either dates or integers or numerics, that sort of thing. And it lets you do lower bounds, upper bounds, range between the two. So for this example, I say star to n. That means the upper bound is n. And I could flip it and say n to star, meaning the lower bound is n. or you could say, you know, S2N, and that will put the range between those two items. Finally, geospatial. So there's a lot of geospatial data out there, lat longs. You can do bounding box queries. You can do radius search queries where you specify the point and then the radius around it. A lot of people actually do some really interesting work with geospatial because at the core, it actually uses spatial for J API. And I've seen other people do some interesting things like doing doing time calculations. I was talking to Tony, and he was talking about doing facial recognition. I think that I could probably come up with something interesting with doing facial recognition using the geospatial search in Leucine. But it is a very powerful API that you can use, and it does it in 3 dimensions too. So, all right. So text analysis. So we know what query capabilities we have, right? So now we need to know how we can get the data into that format, right? And so in Leucine, we need to do that with text analysis. So in our text analysis, what we're going to do is convert a stream of text into searchable words, okay? So I've got a long string. I need to split it up somehow to make sense of it, okay? And so Leucine does this a couple ways. It uses a character filter. What this does is it mutates a single stream of text and then sends it out. So input string, output string, okay? That gets fed into a tokenizer. So a tokenizer splits a string into a stream of strings, okay? So you can split it up. So you have one, and then you have multiple items. And so an example for this is I want to split on white space. And so you split it on white space, and the output is more of that white space. And finally, we've got a token filter. So it has an input of token streams, and it mutates each of those tokens and sends an output of those tokens. Now, it's important to note that it has to go in this order. So a character filter, 0 to n character filters need to be before a single tokenizer, which is followed by multiple token filters, 0 or more token filters. So we're going to actually do some examples here to just get the concepts down. All right. So notable character filter is an HTML strip character filter. So here's my example input text, right? So we see all the paragraph tags, the ahref tags, all that stuff. So if I'm going to mutate this text, what do you think the result should be? Now this is your turn to answer. Somebody yell it out.
Example link.
Example link. Yes, exactly. So this makes sense, right? Fantastic. All right, pattern replace. Who has their regular expression foo going? All right, so testing 1, 2, 3 with this pattern, and I'm going to replace it with an empty string. What? Testing. Right. And the interesting thing with the pattern replace, you can get very interesting by actually having capture groups too. So you can do capture groups and start fiddling with the arrangement. So like I said, learn regular expressions. They are amazing, amazing things. All right, so tokenizers. So we got character filters, right? So character filters, you take a string and output to a string. Now we're going to do a tokenizer, right? So we've got a string input, and now we're going to tokenize it into multiple tokens afterwards. So we've got a keyword. What do you think a keyword would be? Guess? Just somebody throw it out there. There's no stupid answers. What? So a keyword, it just keeps it as a single keyword, right? Maybe you can get the next one. All right. So we have the hello world. We're going to keep it the way it is, right? So there's a couple of reasons for that. Most notably for faceting. So for faceting, you need to preserve the entire token in order to facet on it, because the faceting actually happens on the index terms. So that's one reason why you'd actually have a keyword tokenizer in there. All right, so white space. This seems pretty straightforward, right? So what do you think hello world would produce? Right, exactly. All right, so we're getting it, right? Now, it keeps the exclamation point though. So there's different tokenizers that would start doing that. So standard tokenizer would actually strip out the punctuation. Actually, standard tokenizer will strip all punctuation except for periods in that's preceding text and posts and has text on both sides of it. Preserving acronyms, that's about it. So btf360.com, the dot would be preserved, but everything else would pretty much be split. All right, so next one is patterns. So yes, more regular expressions, right? So we can define our regular expressions and split on our custom regular expressions. And finally, this is important to note that the ICU tokenizer, if you're doing foreign language at all, pretty much just use the ICU tokenizer. It does a very good job. And what that actually does is it finds proper splits based on the language. So Chinese, if you've ever seen Chinese, it's just text, like it's just character after character, and it's just each character is a word. And so if you had white space, well, you're going to have this gigantic term, and it doesn't split properly. So ICU will actually recognize, hey, this is Chinese text, and I need to split on specific tokens or specific characters. All right. So token filters. All right. So we did character filters, string to string. We did tokenizers, string to stream of tokens. And now we've got token filters, which is token stream from the tokenizer into a mutated token stream, right? So here's the lowercase. All right, hello world. Who do you think, what's going to happen here? Yeah, lowercase, right? OK, yeah, so this is getting very, very quick. All right, so this is an interesting one, synonym. So I've got a synonym file with expand set to true, with Japan, JPN, Japan, and JN. So I want to get the ISO country codes for Japan, really. And I want to plug these synonyms in. So if I've got a token stream of to Japan, what do you think the output would be? How about this? All right? So what I'm denoting here with these curly braces is that those are actually going to get stacked vertically. So the offset is still at the same location, but you have two, and then you have Japan, JPN, and JN, because we need to preserve proximity so that our proximity clauses actually still work, right? Because if I want to quote to JN, right, I still want that hit. So we're going to keep that position stacked vertically. All right, so here's a different one. Let's take that same thing, except say expand to false. Now what do you think it's going to be? To JPN. So what this actually does is it expands it to false, so it means if it matches either of those, it goes to the first one and inserts it. All right, so next is word delimiter. All right, so this one's interesting, right? This is my favorite airplane, the F-22 Raptor. That is an awesome airplane. But these signatures are actually somewhat, confusing. So how would somebody want to search on F-22 Raptor? Would F-22 make sense? Would F-22 space Raptor make sense? Would F-22 Raptor all concatenated together make sense? Well, yeah. So I think we can convert it to say, all right, I want to just split on dashes. That's one capability, and you just preserve those two tokens. There's another option where you say, if you're changing from alpha to numeric, split on that. So your F-22 would match that too. And then there's another capability. This will get you in trouble, though. You can say do all those splits, but at the end, I want to concatenate them all together. So your F-22, Raptor, all that stuff will work. Once you start playing with the concatenation stuff, just be careful. We made a mistake by actually doing this like crazy, and it made our index get out of control. So yeah, especially think of what would happen if you had to have links and URLs that do something like that. It gets out of hand real quick. All right, I think this is the last one. So we got the Porter stem. So wouldn't it be nice that if I search for Steve walked to the store, all right, would it make reasonable sense that Steve walks to the store would get the same hit, right? Wouldn't that be expected? So the Porter stem actually goes ahead and does that. So what do you think the Porter stem of these three will actually do, result in? Walk, walk, walk. Yeah. Yeah, so it takes the root stem and will convert them all into the base stem. So you don't have to find the different variants. It's important to note that this is language dependent, okay? So if you've got foreign language stuff, this is a completely different talk in and of itself of how to deal with foreign language and stemming within a foreign language, because you need to start wiring up different languages, because obviously German stemming is going to be different than English stemming, different rules. All right, so we looked at the text analysis, right? So now we know how to split on text, how we can condition our text into searchable terms. So that leads us into the inverted index. So it takes those terms and starts splitting it out, right? So on the left, we have document text, okay? On the right, we've gone through our analysis chain, and now we map each individual term or token and map it to the document ID. Okay, that is the essence of what an inverted index is. Okay, everyone got it? All right, so now that we got it, what do you think the tokenizer was used here? Right, here's the clues. You got a capital IT and you got a IT question mark. Anyone? White space, yes. Now, wouldn't it be annoying to have to search on IT question mark, right? That would be a pet peeve of a user, and case-sensitive searching. That would be also a pet peeve of a user, depending on the situation. But for general text searching, that usually doesn't fly. So we can do better, right? So before we had that, now we concatenate them all, and we change it to IT. Lowercase. So now, who has an idea of what analysis chain we kind of converted into?
Basic punctuation.
Sure. Yeah, so there's multiple ways to skin this cat. So I could have used a standard tokenizer and a lowercase. I could have done a white space tokenizer with a word delimiter token filter with a lowercase token filter. So with these chains, it's very flexible. You can choose how you want to do all this stuff. Another possibility was do a character filter to strip out a question mark with a regular expression, right? It's usually not the best way to go about it, but there are multiple ways to skin that cat.
I have a question.
Yep.
So is inverted index mainly used for like unstructured data? If everything is structured, then I guess this is good for like a Google search, but if you want to do like a fielded search, you can't do that with this, right?
No. So if you're doing a fielded search, each field gets its own inverted index, right?
Oh.
So yes.
Oh.
So you're going to say if you have a title and body, your title field is going to build everything that's in here for just this specific title.
Okay.
So you can still do fielded searches.
When is the use case of doing like an inverted index just versus like a standard index? Like what makes that decision?
Leucine. That is how Leucine works. If you say index this document, you are going to get an inverted index. That's how it works under the hood. You don't specify it. That's just how it works. Okay. All right. So now we know how to split tokens. We know how to query stuff. How do we find the relevant information? Okay. What is relevant? There's this tfidf. This is a very scary word. Term frequency, inverse document frequency. Oh, my head hurts, right? So what we do here, it's not that complicated of an issue. Term frequency. So let's say we have a bag of terms. Okay. So we're going to make stuff more relevant the more it actually hits those terms. So if I've got words all over the place and it matches my document, fantastic. I'm going to boost that up. Inverse document frequency. What that means is I'm going to boost non-popular terms, right? So if there's a unique term, I'm going to boost that up, right? So if I said the dog walked, and a document came back with just the in there 500,000 times, you could say, wow, that's, you know, I could see why that would hit, and your term frequency would hit a lot. But you'd say, yeah, you want to know what? The isn't, you know, that fantastic of a, you know, a differentiator. So how about I find something like dog or something along those lines that is more unique, and I'll boost anything with that to the top. So that's kind of the core capability. That's kind of the core algorithm that we use generally to actually do all that stuff. Yeah.
How do you rank those different words, dog versus the?
So
Specificity and uniqueness.
Yep. So actually internal. So it looks at the entire document corpus, right? So you indexed all your other data, and so it actually knows the term frequencies of all that information. So in the inverted index, you said, hey, here's the term, and here's how many documents I have. It knows how many documents you have. So we just go ahead and say, yeah, it's fine how many there are.
So it's really like as the index grows, that document frequency grows as well. It's not like you train it one time and then it's set.
Yep, exactly. So boosting. Boosting is kind of the secret sauce that a lot of people do, right? So you start with tfidf, and that generally gets you 80% of the way there. Boosting is different though. So if you want to say, I've got some important terms, I can actually perform a weighted average to that. Or you say, hey, I want to search across the title and body field. But if the term is found in the title, boost that 5 times more than the body, because that's more important to me. Right? So we can perform these boostings to actually do that. And finally, signals. So Google has I think it's around 80 different signals that it uses. So an example of signal would be, I know that Jonathan clicked on this document or liked this document from Facebook, right? So, and I know that Jonathan is a friend with me on Facebook, so I'm going to boost this document to the higher up because yeah, he's in my social network, he'd probably be interested in it, right? Or another signal that I've used before, recent documents. So what you can actually do is a lot of math. So I can say, hey, do an exponential decay of the score based on the date of the document. So if it's 1 year old, the score is going to be halved. If it's 2 years old, it's going to be down to a quarter. And we kind of calculate that in so that the further you go out, the less relevant it is for users. And so on, that's kind of where your secret sauce is with boosting and signals processing to determine what is relevant for your specific users. All right, relational versus denormalized. So this is the concept of going from MySQL down into Leucine speak, right? So up here we got students, we got Marina and Ben, shout out, right? We got our classes table, and now we got to have a join table, right? So if we have a lot of these join tables, it gets pretty slow, pretty quick. Maybe not so quick, but once you start getting 10 join tables or so, it's just a dog. In Leucine, what we end up doing is just sticking them all into one table, and they allow you to have multi-valued fields. So we just pass in a collection, and we say index all this, and now it's denormalized into one specific table, and it's fast. And it just goes in the inverted index like normal. All right. So we got the whirlwind approach of Leucine and kind of what it does. Now let's take a step back, take a breather. All right. We're going to talk about higher level languages. All these guys, this is in our look category. And these are all built on top of Leucine. And they all provide web APIs. They all provide distributed search mechanisms. And we're just going to touch on this pretty quick. Blur, I'm just going to talk about. Aaron McCurry wrote this. And this plays in the Hadoop ecosystem pretty well. So this is more of a batch-oriented process. It's not so much near real-time. What you end up doing is you put a bunch of data into HDFS, and you start making MapReduce jobs. And you're going to build one index in a batch form, and you're going to do all your ETL, the transforming and loading and all that stuff into a Leucine index. You build that Leucine index, stick it back into HDFS, and then Blur will actually, once the job is done, it'll make that search searchable, really. This is more once you are in like hundreds of billions of documents. That's when you need to start worrying about it. It's not quite as easy as Solr or Elasticsearch to set up. But yeah, it's out there if you play in that world. A lot of us here, we can play in the Solr versus an Elasticsearch world. So we're going to talk about that a little bit more. So we got Solr. It's been around for a long time now. I think it was about 2006 it came out. It was made by a guy called Yannick. He worked for CNET, so CNET, the review company place. He worked there and open sourced it from CNET. So it went into Apache. It stayed there for a couple of years, and 2008, I think, they merged into the Leucine code base. So they share the same code repository. But you know, they added capabilities for distributed search, but it wasn't easy. It was, you had to manage your shards, and what a shard is you split your index out into multiple machines, and you say, this section of my documents goes here, this section goes here, and this section goes here. And then you have another machine that actually aggregates all those. So it'll say, give me your top 10, give me your top 10, and give me your top 10. And then it does its own scoring to say, OK, here's the real top 10, right? But you had to manage the indexing capability. You had to manage which document went to which shard. We did that. It was somewhat painful. Maybe not that painful, but it definitely was not easy. So in comes Elasticsearch around 2010. They wanted to make distributed search easy, much easier than Solr. I think they were successful with that, with making distributed search easy. But then Solr kind of, the great thing with Elasticsearch is they've kind of shaken up Solr a little bit to say, all right, you guys really need to stay relevant. And so Solr came out in 2012 and came out with Solr Cloud, which is their distributed search engine. It's still, so Solr already had the capabilities to do distributed retrievals. It just wasn't the distributed indexing capabilities that they had in there. So Solr Cloud actually makes that pretty darn easy for you. So some differences, Solr is in the Apache Software Foundation, open source. Elasticsearch is an open source product from a product company. And so they provide some core capabilities, but if you want the goodies, you got to pay for it. So they've got add-on products. Elasticsearch, their gateway drug per se, is their ELK stack, Elasticsearch, Logstash, Kibana. That's what got me playing around with it. And that actually makes log aggregations easy, pulling stuff off your Apache gateway logs and getting a nice UI to play with it. So that's your gateway drug with Elasticsearch that they want to get you. But if you wanted to do SSL or that sort of a thing, you're going to have to pay, I think it's $10,000 or $15,000 per node in your cluster. So it's a little pricey, but Solr, it's free. You can do whatever you want. It's not as polished, I'd say, as the product of Elasticsearch, but it actually works pretty darn well. And you highly customizable. So we customize it a lot, and the capabilities are actually pretty good. I'm happy with Solr. Yeah, so Solr is pretty nice. And yeah, so moving forward, Solr actually, the biggest difference between these two are kind of configuration. So Solr, you need to define your schema up front. Well, not so much anymore. But usually you define how you want to search stuff and think of that as your Hibernate mapping file, and you need to define your application context. That's the Solr config. All those are in XML, and you kind of define that up front. Elasticsearch, you just kind of set it and go. They have something called schemaless mode, which is their default. And schemaless means I'm just going to pass a bunch of text to it, and it's going to do its best to figure out how you want it indexed. Personally, I don't quite enjoy schemaless mode because I want to know exactly how it's going to work. But you can always customize Elasticsearch and define exactly how you want to do it. But once you start doing that, you're kind of, the two are pretty much the same. And you're going to be using YAML instead of XML, and a lot of JSON in Elasticsearch. But that's pretty much it. So to wrap it up, what we want to do is design for the user, right? We want to know how users are going to search for stuff. What capabilities do they not have that we can deliver? How can we make their jobs easier? And to do that, they need to tell us how they want to search and find information. And we need to know what data we have, right? So we need to know our data and know how we can index our data to answer the questions that they're seeking, right? So finally, last point here is be lazy. So just don't create yet another server. So Leucine just gives you the Java jars. That doesn't mean that you're going to be doing distributed searching. That doesn't mean that you're going to be having replication built in, fault tolerance, all that stuff. Be lazy. Use some already pretty darn good tools out there, Elasticsearch and Solr, to answer and provide these capabilities for your users. Any questions? Yep.
I was wondering, at the analysis phase, that was dealing mostly with tokens and text.
Yep.
What do you do for things like a PDF document or an image?
Yep. So what we've done is have an update processor chain. So like Solr actually has, so this is outside of Leucine. So with Leucine, you need to kind of just say, here's my map of stuff, and that's where you go. So Solr actually provides an update processor chain. So our example update processor is we've created a custom processor that downloads documents. And then we get an XML document. And then the next processor, we say, all right, here's a bunch of XPaths to extract all those items out of that XML and insert it into a Solr input document, which is a glorified hash map, really. And so you just build these processors one after another. And then at the end, you just say, OK, go ahead and index now, please, right? Alternatively, you can do this outside of the update processor chain, and you just do that in a different level, right? So for example, Logstash will do all that aggregation, and Logstash will go ahead and put it in the proper format, and then say, OK, here's my fully populated document. Please go ahead and index it. So there's a couple ways, and that's more the ETL phase approach. Yep.
So if you're indexing documents, user gets a hit back, right? They're kind of seeing like maybe a summary of the document that you're pulling back. So where do you store the full documents? Do you store those in the index as well, or are you like fetching them from like a different location after results come back?
So we fetch it from a different data store. Generally, you want to keep your index as small as possible. So you don't want to store everything in your index because you want to provide a lot of speed, you want everything in RAM. But if you store the entire document in the index, it's going to be hard to fit everything in RAM. So that's kind of, we have a different data store where we just say, all right, here's the URL to that data store. Go ahead and download that document for me.
Does that mean, is that data store like a relational database or another index?
So for us, our team, we have a Cassandra database, a data store.